So this is what we were doing last week, and we showed one side of the equivalence, namely, given a DFA, we showed how to arrive at a regular expression by using these expressions R, I, J, K, denoting the sets R, I, J, K, and then showed that the language accepted by a DFA is of this form, RIJK. I mean, it's a sum of expressions of this form, and therefore, it is easy to show by induction that that particular regular expression denotes the language accepted by the DFA. So today, so this is done. Today we'll go the other way. We'll take a regular expression and we'll arrive at a finite automaton, and it'll turn out that it's easier if we use epsilon NFA to do that. And this is the only reason why epsilon NFA were introduced, because it makes this proof easier. But we have seen that DFA, NFA, and epsilon NFA have the same expressive power. They all accept the same class of languages, namely the regular languages. So there's no problem here. You can always convert an epsilon NFA into an equivalent DFA, right? So this proof is much easier. I mean, it's easy to figure out because let me first write down the theorem formally. So the theorem says let R be a regular expression then there exists an epsilon NFA say M, which accepts the language denoted by the regular expression. Okay, and this proof is simple. It is by induction, by structural induction, by induction on the structure of R. So if you recall, how were regular expressions defined? They were defined by induction. So there were three base clauses. Okay, but before we come to that, let me complete this sentence. We show that LR equals LM for some epsilon NFA M, which has some additional properties, which satisfies the following properties. It has exactly one accepting state. Two, there are no transitions into the initial state. Three, there are no transitions out of the accepting state. No transitions out of the, and we say the because there is only one accepting state. It makes it much easier if we can show that, right? So it'll often turn out that when you do, and this is a general remark, not just about this proof, often when you are proving some result by induction, you have to strengthen the result that you want to prove for the induction to go through. Okay. So often what you are going to prove by induction is stronger than the result that you want, meaning that what you prove by induction will imply the result that you wanted to prove. Okay. So here we are saying not only is there an epsilon NFA, which accepts the language denoted by R, but it also satisfies these three conditions. Okay, so this is a stronger statement. Anyway, so let's do the proof. What is the basis of the induction? Remember, what are the clauses defining a regular expression? So first we had, these are regular expressions, right? Epsilon, empty, and a symbol A, right? So what is an epsilon NFA which accepts the language denoted by epsilon? Anyone? So these are the regular expressions, and we want epsilon NFA for each of these. Can you give an epsilon NFA for which accepts
NFA with only one state, which is an accepting state.
right? Only one state, which is an accepting state, and it satisfies all these three properties. Exactly one accepting state, no transitions into the initial state, and no transitions out of the accepting state. So it's satisfied. What about this one, empty?
Only the initial state, no final state.
Right.
Uh, but it should be having exactly one accepting state, no, sir. Okay.
You're right. So it's clear, right?
Yes, sir.
All these three properties are satisfied. Now we come to the inductive part, right? And there are various cases. Right? Case one, R is R1 plus R2. And let's assume that the epsilon NFA M1 satisfies I mean, accepts the language denoted by R1, and similarly for M2, right? So we assume this. And further assume that M1 and M2 also satisfy these three constraints. That's important. That's the induction hypothesis. Right? That's important. Okay, so here is M1, right? I'll just draw pictures here. All this can be done formally, but it's such a waste of time for such an easy result. And we have much more difficult results that we should discuss in more detail. So this is M1. One initial state, one accepting state. This is M2. One initial state, this is Q2, huh? And one accepting state. So what should an NFA that accepts LR1 union LR2 look like? Any idea?
Link the initial state with epsilon and final state with epsilon and remove one of the final states and initial states.
Yes. So what we have to do is do some surgery here. So let me draw it again. We could have just added an initial state here, a new initial state Q0. And added these transitions. And we would indeed get an epsilon NFA that accepts LR1 union LR2. But why is this not sufficient?
We need one final state.
Yes, we need one final state for the inductive proof to go through, right? Because this NFA will be used in a bigger proof, right? Because we are working by structural induction. So what we have to do is to add a new final state. I'm not going to draw another figure. Add these epsilon transitions. And these will become non-final. So I'm not drawing it again. It's clear what we should do. So, of course, one needs to prove that this epsilon NFA will accept LR1 union LR2, but that's easy. I mean, we'll not do such easy proofs in this course. So is this clear? Case 2. R equals R1 followed by R2, or dot, if you want, right? So this will be like the automaton So these are epsilon NFA such that Ri is LMI, and each Mi satisfies the three conditions. So it's the same thing. So it's just M1 followed by M2, right? So here's M1. Whatever. This is M1. And this is M2. And all you need to do is just add this epsilon transition from here to there and make this non-final. And again, you can show that all the three conditions are satisfied at this bigger epsilon NFA accepts the language LR1 dot LR2. Okay, and finally we come to Kleene star. This should be R1 star. Okay. So here's M1. Q1, F1. Right? So this is the initial state and this is the final state, right? Well, we may think that it is enough to add this epsilon transition. But it is not enough. First of all, now we have a transition going into the initial state, and we want to avoid that. Can you quickly tell me why we want to avoid that? I mean, we assume these three things for a reason. Okay? There is a reason why we put these three constraints. There is a reason behind everything. So what would go wrong if we didn't require that there is exactly one transition going into the initials? Sorry, there are no transitions going into the initial state. And similarly, what would go wrong if we didn't assume that there is exactly one accepting state or no transitions out of an accepting state? We should think about these things. Why did we assume those things? Is it really necessary? Yeah. Okay. Let me just say what you need to do. You need to put a new initial state to satisfy those constraints and a new final state. And there's an epsilon transition here. And also this. So any idea So this is the correct construction, but why do we need to do all this? Well, just take an example. What example should I take? Should I take a very simple example first? Take R equals A star, right? So here R1 is A, right? So LR1 is the singleton set, this. So M1, this is M1. Right? This is M1. Now, if we just added this epsilon transition, right, and call it M, let me, since we have modified M1, let me call it M. So the question is, will this suffice? So why is the answer no?
Because epsilon can be accepted.
Right. So LR contains epsilon. Okay. On the other hand, so you got to distinguish between two cases. Maybe R1 itself, the language generated by R1 itself had epsilon, and then you should preserve it. And if it didn't have epsilon, of course, you have to add. So that is why you got to add these new finals, this new initial state. Okay, so this is where you need a new initial state, and it helps if the initial state has no incoming transition. Okay, this example doesn't really explain it, but there are other examples to show why you need an initial state with no incoming transitions. Okay, it is you can easily, in fact, you should try to do this exercise. You should show that if any of these three properties does not hold, then if you apply the same construction, it'll not work. So you can come up with examples to show that. Okay. But at this point, I'm not going to do that. Okay. And you'll also find examples in the book. But it's always better to find out things for yourself. Why these are needed, right? There is an alternative definition of NFA and epsilon NFA where you have more than one initial state. If you have a set of initial states, then things become a little easier. But we'll just stick to what this book says and go by this definition. Okay. In any case, the fact that these constructions are correct can all be proved, although we are not going into the proof. We are just appealing to intuition here. The proofs are long and boring, but they're there in the book, and I think you should go through them. Okay. So any other questions?
Yes, sir, I have.
And just one moment. Let me write this down. Yeah, tell me.
Sir, actually, the thing is that the epsilon transition is from the final state to initial state, and it can go back to the final state only if it is accepting the, symbol A. Then in that case, why the regular language is accepting epsilon? And secondly, what should be the actual state so that it only accepts the, A and all, but not the epsilon? So
By definition, of regular expression, one of the inductive clauses is R equals R1 star. The language denoted is LR equals LR1 star. This is part of the inductive definition of regular expressions. And by definition, L star is the union of all Li, where I ranges over the natural numbers. So you can either write I belongs to n or I greater than equals 0. Okay. And L0 is just epsilon. L1 is L, and L2 is L concatenated with L, and so on, right? So epsilon is included. That all that is by definition of the Kleene star. So does it answer your question?
yes, sir. Thank you.
Okay. Now it turns out that for the same regular language, there may be many different regular expressions, right? All those different regular expressions, they denote the same language. In that case, they are called uh, equivalent. But if we think of two regular expressions as being equal, so to speak, if they denote the same language, then there are some algebraic laws which are satisfied by regular expressions. For example, commutativity. Okay, so it doesn't matter whether you write R1 first or R2 and then R2, or R2 first and then R1. Why? Because union is commutative. So LR1 union LR2 is the same as LR2 union LR1. Similarly, union is also associative. So if you have regular expressions R1 plus R2 and then plus R3, this is the same as, meaning they denote the same language. this regular expression, right? So all this follows from the associativity of union. You also have associativity for dot. Or concatenation, which says that if you concatenate R1 and R2 and then R3, that is the same, meaning they denote the same regular language as concatenating R2 and R3 first, and then concatenating the result with R1. And then there are some identity laws. So for instance, the empty symbol is the identity for addition. So empty plus R is R plus empty equals R, because the empty set is the unit for union, for the union operation. And similarly for concatenation, you have epsilon dot R equals R dot epsilon equals R, right? Then we have something called an annihilator. So empty is the annihilator, both the left and right annihilators. So you have empty followed by R. Let me write down the name first. And then there's distributivity of dot over addition on both sides. And all these, of course, follow from the set operations. So they're not surprising at all. So R2, R3. And then we have idempotence of addition, of course, not of multiplication. And then we have closure, which means that all these operations are closed. So anyway, the algebraic structure here is called a semi-ring. And it's a fascinating topic, namely whether these equations are enough to characterize all equalities between regular expressions. That is known as completeness. So that's a fascinating topic, and we are not going to go into that. I just mentioned this, right? So this is not included in the course. Those interested in research in this field will come across these things later. Okay, so at this point, let me take a pause and ask you if you have any doubts so far regarding automata and regular expressions, and regular languages and regular expressions. Any doubts? Okay, let us proceed then. So what have we done so far? We have seen this is what we have seen. Regular languages have 4 different characterizations or descriptions. What are those 4? Well, GFA, NFA, epsilon NFA, and regular expression. By the way, later on in the course, when we use RE, after we have introduced Turing machines, RE will stand for recursively enumerable. So just to, well, of course, right now you don't know what those are. So for now, RE stands for regular expressions. Okay, so we have seen all these 4 descriptions or characterizations of regular languages. And in order to show that something language is regular, you can use any of these techniques or tools or artifacts to do that, right? So to show that a language is regular, you can give a DFA or NFA or epsilon NFA that accepts the language, or you can give a regular expression that denotes the language. Of course, you have to give a proof that your claim is correct. But that is how it works. But it turns out that not every language is regular. And we already know why this is the case, right? Because the set of languages is uncountable over any alphabet which is non-empty. The set of languages is uncountable, right? Whereas the set of regular languages is countable because you can enumerate all the regular expressions. So that's not a problem, right? Over a finite alphabet. So not every language is regular. And how do we show that a language is not regular? None of the things we have seen so far will help us do that. I mean, how do you show that there is no DFA which accepts a given language? It's easier to show that a DFA accepts a language, a given language, than to show that there is no DFA which accepts a given language, right? So to do that, we are going to show an important property of regular languages and use that property to show that some given language is not regular. Okay, so here's the theorem. And it is extremely important. It is a very powerful tool for showing that a language is not regular. And this theorem is known as the pumping lemma. for regular languages. And the statement of the theorem is extremely important. You must know it by heart. And you must also understand it, because it takes a little while to really figure out the true meaning of the lemma. So let us go slowly over the statement of the lemma. We'll of course prove it, because this is an important result. So let L be a regular language. Okay. Then there exists a constant n, which depends on L, of course. Such that for every string W in the language, with the length of W being greater than equal n, we can break. I think a better way is to write, it is possible to decompose W, but I'll just stick to this. W into 3 strings as W equals X, Y, Z, such that there are 3 constraints. Y is not empty. Number 2, XY, the length of XY is less than equal n. And 3, X, Y to the K, Z belongs to L for all K greater than equals 0. And if you want to write it in words, that is, we can always find, a non-empty string Y satisfying 2, the condition 2. One says it's non-empty. Condition 2 says the length of XY is less than equal n. That can be pumped. An arbitrary number of times or deleted. number of times or deleted when k equals 0. And the resulting string is again in L. Okay, we don't have much time left, but let us just carefully go through the statement of the lemma. It's so important to understand the theorem, the pumping lemma, because so many things can be proved based on this lemma. Now, let me explain why people find it difficult to understand and apply the lemma. The reason it is difficult is because there are so many quantifiers in this state, and the quantifiers are all nested. Okay. So when you say let L be a regular language, this really means this is true for all regular languages. So there is an implicit nesting of quantifiers here. And that is why people find it so difficult, because people always find quantifier reasoning difficult. I mean, this is from my experience, not some, theory, right? So at the topmost level, you have for all languages which are regular. So I'm not writing the regular part, right? Then next, there exists a constant n, right? Which depends on n, such that for every string w, with certain constraints, right? So I'm not writing those constraints. We can break w. So that is another, we can break. Huh? This is important. We can break means it is possible to break. Right? Or there exists some way of breaking. So this is again another quantification over x, y, and z, such that blah, blah, blah. And that blah, blah, blah also involved another quantification for all k. Yes, and that is why it is so difficult for beginners to really fathom what's going on here. Okay, so I advise you to spend some time just understanding the statement of the theorem, and maybe today, instead of trying to prove it, let us apply the pumping. Let us try to apply. We'll see the proof in the next class. Let us try to apply the pumping lemma. We may not even have time for that. Just 3 minutes left. So let me just give a hint of how to apply the pumping lemma in this case. So let us take this example, which is this language, L, which has n0 zeros followed by n ones for all n. And we can take n greater than equal 1 or 0, it doesn't really matter. Okay, so L is, epsilon. If it has 1 0, it'll be followed by 1 1. If it has 2 zeros in the beginning, it'll have 2 ones, and so on. Right? So so show that this language is not regular. But we don't have time to do that. So we'll do it in the next class. If you have any quick questions about the lemma or the statement of the lemma, you can ask me right now. As we have just a minute left. Any doubts about the statement? This is the length of W, by the way. Depicted by that modulus symbol. So this is the length of W. So any questions? Any doubts about the statement? Okay, so let us stop there. And we'll continue in tomorrow's class.